please subscribe to support the channel. Stop for a second and think about this. Right now, as you're watching this video, you're hurtling through space at over 500,000 miles per hour. Not just because Earth is spinning or because we're orbiting the sun. No, our entire solar system is screaming around something so monumentally huge that it takes us 225 million years just to go around it once. The last time we were in this exact spot in space, dinosaurs were just starting to walk the Earth. And here's the really wild part. Despite living inside this thing our whole lives, despite ancient humans staring up at it for thousands of years, we only figured out what it actually was about a century ago. We call it the Milky Way, and trying to wrap your head around just how big it is might be one of the most mind-bending things you'll ever attempt. But let's try anyway, because the story of how we measured something so incomprehensibly vast while stuck inside it is one of the greatest detective stories in human history. We are, in the most literal sense, cosmic dust. Our planet is a tiny blue dot, as Carl Sagan so eloquently described it, suspended in a sunbeam floating in an ocean of darkness. But pull back from that perspective, zoom out beyond our moon, past Mars, beyond the gas giants Jupiter and Saturn, out past the icy realms where Pluto drifts in perpetual twilight, and you begin to see that our solar system is just one among billions. Keep pulling back, and the sun itself becomes just another point of light, then fades into a sea of stars so dense and numerous that individual points begin to blur together. This is our galaxy, and the question that has puzzled humanity for centuries is deceptively simple. Just how big is this cosmic structure we call home? How do you measure something so vast that light itself, traveling at 186,000 miles every single second, takes tens of thousands of years to cross from one side to the other? How do you map a territory when you're trapped inside it, when cosmic dust obscures your view in every direction, when the very scale of what you're trying to measure defies every intuition evolution has given you? This is the challenge that generations of astronomers have faced, and the story of how they met it is one of humanity's greatest intellectual achievements. For our ancient ancestors, the Milky Way was a mystery wrapped in mythology. Cultures around the world looked up at that ghostly band crossing the heavens and wove stories to explain its presence. The ancient Greeks believed it was literally milk, spilled across the sky by the goddess Hera. The name we use today, Milky Way, comes directly from this myth, via galaxis, the Greek word for milky circle. In Chinese astronomy, it was seen as the Silver River, a celestial barrier separating two lovers in an eternal cosmic tragedy. Norse mythology imagined it as the path souls took to reach Valhalla. Aboriginal Australian culture saw it as a smoky trail of a cosmic fire. Every civilization that looked up created its own narrative to explain this mysterious luminous path. But none of them understood what they were truly seeing. They couldn't have known that they weren't looking at some celestial phenomenon happening above them, but rather that they were seeing the combined light of billions of stars, most of them so distant that their light had been traveling through space for thousands of years before entering their eyes. The ancient observers couldn't have imagined that they were living inside the structure, that the band of light was our view of the galactic disk from our position within it. This insight perspective created a fundamental problem that would plague astronomers for millennia. Imagine trying to understand the layout of a vast city while standing in the middle of it on a foggy day, unable to climb to any high vantage point, unable to leave the city limits, unable to see more than a few blocks in any direction. Now imagine that the city is thousands of times larger than Earth itself, that the fog is made of dust and gas scattered between the buildings, and the buildings themselves are stars burning with nuclear fire. This was a challenge facing anyone who tried to understand the true nature and scale of the Milky Way. For thousands of years, the best minds in astronomy had no idea whether they were looking at a thin layer of stars coating the inside of a sphere with Earth at its center, or whether they were part of some larger structure. The philosophical implications were profound. If we were at the center of everything, that suggested a special place in the cosmic order. If we were just somewhere in the middle of a larger structure, that implied something very different about our cosmic significance. The first real breakthrough in understanding the Milky Way came in the year 1610 when an Italian mathematician and astronomer named Galileo Galilei pointed a new invention, the telescope, towards the heavens. What Galileo saw that winter night would begin to unlock the mystery of the Milky Way's true nature. When he trained his primitive telescope on the pale band crossing the sky, he made a startling discovery. The Milky Way wasn't a cloud at all, wasn't a river of milk or smoke or anything continuous. Instead, Galileo saw that it was composed of countless individual stars, so numerous and so faint that to the naked eye they blurred together into what appeared to be a glowing mist. He wrote in his book Sidereus Nuncius, or Starry Messenger, that the galaxy consisted of a mass of innumerable stars planted together in clusters. This was revolutionary. For the first time in human history, someone had evidence that the Milky Way was made of the same stuff as the points of light scattered individually across the night sky. It was just that there were far, far more of them than anyone had imagined, packed so densely in that band that they created an illusion of continuous light. But Galileo's discovery, while groundbreaking, only opened up more questions. If the Milky Way was made of stars, how many were there? How far away were they? Were they scattered randomly through space, or did they form some kind of structure? And most importantly, what did this tell us about the size and shape of the universe itself? These questions would occupy astronomers for the next 3 centuries, and the answers would prove far stranger than anyone in Galileo's time could have imagined. The problem was that measuring cosmic distances is incredibly difficult. You can't simply stretch a measuring tape across space. Instead, astronomers had to develop clever techniques, using mathematics, physics, and careful observation to infer distances to objects they could never hope to visit. For nearby stars, they could use parallax, the apparent shift in a star's position as Earth moves around the sun, to triangulate distance. But this technique only worked for relatively nearby stars. For more distant objects, they needed to find standard candles, objects whose true brightness they could determine, allowing them to calculate distance based on how dim they appeared from Earth. As telescopes improved throughout the 18th and 19th centuries, astronomers began to build increasingly sophisticated models of the Milky Way. William Herschel, working in the late 1700s, attempted to map the galaxy by simply counting stars in different directions, assuming that if he saw more stars in one direction, the galaxy must extend farther in that direction. He concluded that the Milky Way was a flattened disk of stars, and in this, he was fundamentally correct, though his estimates of its size were far too small. He also placed the Sun near the center of this disk, which we now know is incorrect. But Herschel was working with the tools available to him, and his attempt to systematically map the cosmic landscape was a crucial step forward. His son, John Herschel, would continue this work, expanding the catalog of stars and nebulae, those fuzzy patches of light that could be seen through telescopes but whose nature remained mysterious. Were these nebulae clouds of gas within our Milky Way, or could they be something else entirely? Some astronomers began to suspect that these spiral-shaped nebulae might be island universes, separate galaxies beyond our own. But without a way to measure their distances, this remained pure speculation. By the early 20th century, the debate about the nature of the Milky Way and the broader universe had reached a critical point. Astronomers had observed spiral nebulae, beautiful pinwheel-shaped structures scattered across the sky, but they couldn't agree on what they were seeing. The question came to a head in what has become known as the Great Debate, a public discussion held at the Smithsonian Museum of Natural History on April 26, 1920. On one side was Harlow Shapley, a brilliant astronomer who had recently revolutionized our understanding of the Milky Way's size by studying globular clusters, dense, spherical collections of ancient stars that orbited the galactic center. Shapley had discovered that these clusters were distributed in a sphere around a point thousands of light years from where the Sun sat, and he correctly concluded that this must mark the true center of the galaxy. This meant the Sun wasn't at the galaxy's center at all, but rather out in the suburbs, some distance from the core. Shapley's measurements suggested the Milky Way was far larger than previously thought. He estimated it at about 300,000 light-years across, which turned out to be an overestimate but was in the right ballpark compared to earlier guesses. Shapley's view of a vast Milky Way led him to conclude that the spiral nebulae must be relatively small objects within our own galaxy. If the Milky Way was as enormous as he calculated, it could easily contain these spirals as minor features. On the other side of the debate was Heber Curtis, who argued that the spiral nebulae were actually separate galaxies, island universes comparable in size to the Milky Way, but vastly distant from it. Curtis had evidence that some of these spirals contained novae, stellar explosions, that appeared much fainter than novae observed in the Milky Way, suggesting they were much farther away. He also argued that the Milky Way was much smaller than Shapley believed, perhaps only 30,000 light-years across. Both astronomers presented their evidence and arguments, but neither could definitively prove their case. The observational tools available in 1920 simply weren't powerful enough to settle the question. The audience that night left without a clear winner, and the astronomical community remained divided. What they needed was a definitive measurement of the distance to at least one spiral nebula. If these objects were inside the Milky Way, their distances should be measurable in thousands of light-years. If they were separate galaxies, the distances would be vastly greater. The resolution to the Great Debate came just 4 years later, in 1924, through the work of an astronomer named Edwin Hubble working at Mount Wilson Observatory in California. Hubble had access to the Hooker telescope, at that time the largest and most powerful telescope in the world, with a mirror 100 inches in diameter. With this instrument, Hubble was able to resolve individual stars in the Andromeda Nebula, one of the brightest and most prominent of the spiral nebulae. Among these stars, he identified a type called Cepheid variables, stars that pulse with a regular rhythm, brightening and dimming in a predictable pattern. The crucial thing about Cepheid variables was that their pulsation period was directly related to their true brightness. An astronomer named Henrietta Swan Leavitt had discovered this relationship years earlier while studying Cepheids in the Small Magellanic Cloud. This meant that by measuring how fast a Cepheid pulsed, you could calculate how bright it truly was, and by comparing that to how bright it appeared from Earth, you could calculate its distance. When Hubble performed this calculation for the Cepheids in Andromeda, he got a shocking result. The distance was approximately 900,000 light-years, far beyond even Shapley's generous estimate of the Milky Way size. Later refinements would push this distance even further, to about 2.5 million light-years. Andromeda wasn't a nebula within our galaxy. It was an entirely separate galaxy, a vast collection of hundreds of billions of stars, comparable or even larger than the Milky Way itself. Hubble's discovery transformed astronomy overnight. The universe had suddenly become vastly larger than anyone had imagined. If Andromeda was a separate galaxy, then so were the thousands of other spiral nebulae scattered across the sky. Each one was a cosmic metropolis of stars, and the space between them was almost incomprehensibly vast. But Hubble's discovery also had implications for understanding the Milky Way itself. If Andromeda was roughly comparable to our galaxy in size and structure, that provided a template for what we should expect. Astronomers could study Andromeda from the outside, seeing its overall structure in a way impossible for the Milky Way, and use that knowledge to infer the structure of our own galaxy. It was like trying to understand what your house looks like from the street when you've only ever seen it from inside, and then suddenly being shown a photograph of your neighbor's nearly identical house. From studying Andromeda and other spiral galaxies, astronomers confirmed that the Milky Way must be a spiral galaxy too, with similar structures and dimensions. This forced a recalculation of the Milky Way's size. Shapley's estimates were too large, but the galaxy was still enormous. Measurements gradually converged on a diameter of around 100,000 light-years for the visible disk. Understanding the basic structure of the Milky Way required piecing together observations made from our embedded position within it. Imagine trying to understand the architecture of a building while standing inside a crowded room on the middle floor, unable to go outside or even approach the windows. You might hear sounds from above and below, notice the spacing of the walls around you, feel the building sway slightly in the wind, but assembling all these clues into a comprehensive blueprint would be extraordinarily difficult. This is analogous to what astronomers faced in mapping the Milky Way. Through decades of careful observation and theoretical work, a picture gradually emerged. The Milky Way is what astronomers classify as a barred spiral galaxy, given the designation SBC in the Hubble sequence of galaxy classification. The core of the structure is the galactic bulge, a roughly spherical or ellipsoidal concentration of stars at the very center of the galaxy. This bulge is densely packed with stars, most of them old and red, formed billions of years ago when the galaxy itself was young. The density of stars in the bulge is far greater than in the regions where we live. If Earth orbited a star in the galactic bulge, the night sky would be spectacularly crowded with stars, some appearing bright enough to cast shadows at night. Extending from the central bulge is the galactic bar, a rectangular structure of stars, gas, and dust that rotates as a solid unit, more or less. This bar is approximately 27,000 light-years long and about 7,000 light-years thick, and it rotates with a different period than the disk around it, creating complex dynamics. The bar wasn't even confirmed to exist in the Milky Way until relatively recently. Infrared observations in the 1990s finally provided clear evidence of its presence, something that's easy to see in other spiral galaxies, but difficult to detect from our position inside the Milky Way. Attached to the ends of this bar are the spiral arms, vast arcing structures that wind outward from the central regions. These arms aren't solid structures like the arms of a propeller, but rather density waves, regions where stars, gas, and dust bunch up temporarily as they orbit the galactic center at different speeds. Think of them like traffic jams on a highway that persist even though individual cars are constantly moving through them. The spiral arms are where most of the galaxy's star formation occurs because they're where gas clouds get compressed enough to collapse and ignite new stars. The newly formed massive blue stars that populate these arms are incredibly bright, making the spiral arms stand out prominently in photographs of other galaxies, glowing blue and brilliant against the yellower light of older stars in the disk and bulge. All of this, the bulge, the bar, the spiral arms, is embedded in a thin disk like fillings in a cosmic crake. This disk is where most of the galaxy's visible matter resides, and it's remarkably flat. The disk contains not just stars, but vast clouds of gas and dust, the raw material for future generations of stars. Surrounding everything is the galactic halo, a roughly spherical distribution of sparse matter that extends far beyond the visible disk. The halo contains old globular clusters, the same objects Shapley studied to determine the galaxy's center, along with scattered ancient stars and mysterious dark matter that makes up most of the galaxy's actual mass. The halo is much less dense than the disk, but it's far larger, meaning the total volume it occupies is immense. Within this structure, approximately 200 billion to 400 billion stars orbit the galactic center, each following its own path, each a potential sun for planets, possibly for life. Our sun is just one of this multitude, distinguished only by its proximity to us and by the fact that it happens to have nurtured a planet where conscious beings evolved who could look out and wonder about all of this. So how big is this structure? What are the actual numbers we can assign to the Milky Way's dimensions? The most commonly cited figure for the diameter of the galactic disk is 100,000 light-years, though some measurements push this to 120,000 light-years or even slightly beyond, depending on where exactly you define the edge. But what does light-year actually mean? It's easy to say the phrase without grasping the staggering distance it represents. A light-year is a distance light travels in 1 year, moving at its constant speed of approximately 186,000 miles per second, or about 300,000 kilometers per second. In 1 second, a beam of light could circle Earth's equator more than 7 times. In 1 year, traveling at this unimaginable speed without ever slowing down, light covers about 5.88 trillion miles, or about 9.5 trillion kilometers. This is 1 light year. The nearest star to our sun, Proxima Centauri, is about 4.2 light-years away, meaning the light we see from it today left that star over 4 years ago. When you look at that star, you're not seeing it as it is now, but as it was in the past. You're literally looking back in time. The Milky Way's disk stretches for 100,000 of these light-years from one edge to the other. If you could somehow travel at the speed of light, the absolute cosmic speed limit according to Einstein's relativity, it would take you 100,000 years to cross from one side of the galactic disk to the other. But no physical object with mass can actually reach light speed. The fastest spacecraft humans have ever built, the Parker Solar Probe, travels at about 430,000 miles per hour at its peak velocity, which sounds incredibly fast until you realize this is less than 0.07% of light speed. At that rate, it would take about 20,000 years just to reach the nearest star and millions of years to cross the galaxy. The distances involved are so vast that they mock our intuitions about travel and space. We evolved on a planet just 8,000 miles in diameter, where the farthest points are never more than 12,000 miles apart as a crow flies. Our brains simply aren't wired to grasp distances millions of times larger. But this is the scale of our galaxy. 100,000 light-years from edge to edge, a distance so vast that light itself, the fastest thing in the universe, takes 100 millennia to traverse it. But the disk isn't just wide, it has a specific shape, and that shape is crucial to understanding the galaxy's nature. While the disk extends for 100,000 light-years across, it's only about 1,000 light-years thick for most of its expanse. In the central regions near the bulge, it thickens to perhaps 3,000 light-years, but out in the suburbs where we live, it's remarkably thin. This means the ratio of the disk's diameter to its thickness is about 100 to 1. To put this in perspective, imagine a crepe or a thin pancake 12 inches across. If the Milky Way were scaled down to that 12-inch diameter, the disk would be only about 1/10 of an inch thick, thinner than a couple of credit cards stacked together. This extreme flatness is the result of angular momentum. When the galaxy formed from a collapsing cloud of gas billions of years ago, that gas had some rotation. As it collapsed under gravity, conservation of angular momentum caused it to spin faster, just like a figure skater pulling in their arms to spin more rapidly. The rotation created centrifugal effects that resisted collapse in the plane of rotation, but allowed collapse perpendicular to that plane, resulting in a flattened disk. All the stars and gas in this disk orbit the galactic center in roughly the same direction, all following paths that lie approximately in the same plane, creating the thin disk we observe. Our Sun, and therefore our entire solar system, sits within this disk, located in what might be described as the galactic suburbs. We're approximately 26,000 to 28,000 light-years from the galactic center, depending on which recent measurement you trust. The uncertainty of a couple thousand light-years reflects both the difficulty of measuring their distance to the center and the fact that the center isn't a precisely defined point. This puts us roughly halfway out from the center to the edge, though slightly closer to the center than to the outer rim. More precisely, we're located in a minor spiral arm called the Orion Spur or Orion Arm, a smaller branch that connects two of the galaxy's major spiral arms. The major arms have names too: the Perseus Arm, the Sagittarius Arm, the Norm Arm, and our local Orion Spur bridges the gap between the Sagittarius and Perseus arms. From our position, when we look toward the constellation Sagittarius, we're looking toward the galactic center, though thick clouds of dust prevent us from seeing the center directly in visible light. When we look in the opposite direction, toward the constellations Taurus and Auriga, we're looking outward toward the galaxy's edge and beyond, toward intergalactic space. This suburban location is actually quite fortunate for the development of life on Earth. Closer to the galactic center, the density of stars is much higher, which means gravitational interactions and close passes between stars would be more common. Such interactions could disturb the orbits of comets in a solar system's outer reaches, potentially sending them plummeting toward the inner system where they might impact planets. The galactic center is also home to the supermassive black hole and various high-energy phenomena that emit dangerous radiation. Out here in the suburbs, we're far enough from the center to avoid most of these dangers, but not so far out that the density of heavy elements necessary for building rocky planets and biological molecules, is too low. Stars in the central regions have experienced many generations of stellar evolution, each generation producing and dispersing heavy elements, while stars in the outermost regions have fewer generations behind them and thus fewer heavy elements available.
We're in something of a sweet spot, a habitable zone not just around our star, but within the galaxy itself, sometimes called the galactic habitable zone. The calm, relatively stable environment of the Orion Spur has allowed our solar system to orbit the galaxy for billions of years without major disruptions, giving life on Earth time to evolve from single-celled organisms to technological civilization. But our position in the galaxy isn't static. Everything in the Milky Way is in motion. Our solar system is orbiting the galactic center at an astonishing velocity of roughly 515,000 miles per hour, or about 230 kilometers per second. Despite this enormous speed, our orbital period, the time it takes to complete one full orbit around the galaxy, is approximately 225 to 250 million years. Astronomers sometimes call this period a galactic year or cosmic year. Think about what this means. The last time our solar system was in approximately its current position in the galaxy was about 225 million years ago, during the Triassic period on Earth, when the first dinosaurs were just beginning to evolve. The dinosaurs rose, dominated Earth for over 150 million years, and were wiped out by an asteroid impact 66 million years ago, all during less than one galactic year. The dinosaurs never completed a single orbit of the galaxy during their entire reign. Humans evolved within just the last few million years, a tiny fraction of a galactic year. All of recorded human history, every empire, every war, every achievement of civilization has occurred while the solar system has moved through only about 1/500th of its orbit. We are latecomers on a cosmic journey that has been continuing for billions of years, passengers on a planetary ship that is itself a passenger on the solar system, which orbits within the vast rotating disk of the Milky Way. The sheer scale of this rotation creates challenges for mapping the galaxy. Not only are we trying to map a vast structure from inside it, but the structure is rotating at different rates at different distances from the center, creating what's called differential rotation. Stars closer to the center orbit faster than those farther out, not because they're moving at higher speeds necessarily, but because they're following tighter orbits. This means that the relative positions of stars in gas clouds are constantly shifting over time. Features that appear associated in space might actually be at very different distances, just happening to line up from our perspective, or they might be truly associated but will drift apart over millions of years as differential rotation pulls them in different directions. Additionally, our view of the galaxy is severely obscured by interstellar dust. These tiny particles, smaller than the particles in cigarette smoke, don't absorb and scatter light equally. They affect blue light more than red light, and they block visible light much more effectively than infrared or radio waves. Looking toward the galactic center in visible light, we can see only about 1% of the way there before the dust completely blocks our view. It's like trying to see through fog or smoke. The dust is concentrated in the galactic disk, particularly in the spiral arms where star formation is occurring, which means our view within the plane of the disk is much more obscured than our view looking up or down out of the plane.
For centuries, this dust frustrated attempts to map the galaxy. Astronomers could count stars in various directions, but they couldn't tell if they were seeing fewer stars in a particular direction because the galaxy didn't extend as far in that direction, or because dust was blocking the view. The breakthrough came with the development of radio astronomy in the mid-20th century. Radio waves penetrate dust clouds easily, allowing astronomers to map the distribution of hydrogen gas throughout the galaxy using the 21-centimeter line emission. Hydrogen atoms occasionally flip their electron's spin state, emitting a photon with a wavelength of 21 centimeters, a radio wave. By mapping this emission across the sky and measuring its Doppler shift to determine the velocity of the gas, astronomers could begin to trace out the spiral structure of the Milky Way. Infrared astronomy, which developed alongside radio astronomy, provided another window through dust-obscured regions. Infrared light, with wavelengths longer than visible light but shorter than radio waves, can penetrate through moderate amounts of dust, allowing astronomers to see stars and structures hidden in visible light. The development of space-based infrared telescopes, which escape the interference of Earth's atmosphere, revolutionized our view of the galactic center and other dust-enshrouded regions. Modern techniques for mapping the galaxy have become increasingly sophisticated. The European Space Agency's Gaia mission, launched in 2013, has been creating the most detailed three-dimensional map of the Milky Way ever produced. Gaia measures the positions, distances, and motions of over 1 billion stars with unprecedented precision.
The spacecraft uses the parallax method, measuring how stars' apparent positions shift as Gaia orbits the Sun, but with such accuracy that it can measure parallax for stars thousands of light years away. For each star, Gaia doesn't just determine its position, but also its proper motion, how it moves across the sky, and, for many stars, its radial velocity, how fast it's moving toward or away from us. Combining all this information creates a dynamic three-dimensional picture of the galaxy, showing not just where stars are, but how they're moving. This data has already led to numerous discoveries, including streams of stars being tidally stripped from small satellite galaxies as they merge with the Milky Way, and unexpected patterns in stellar motions that hint at past gravitational disturbances from other galaxies passing by or merging with ours. Gaia's data releases, which occur periodically as more observations are processed, have become major events in astronomy, each one refining our understanding of galactic structure and dynamics. Despite all these sophisticated techniques, pinning down an exact count of stars in the Milky Way remains surprisingly difficult. Current estimates place the number somewhere between 100 billion and 400 billion stars, a range that reflects genuine uncertainty rather than sloppy measurement. The problem is that most stars in the galaxy are small, dim red dwarfs that are extremely difficult to detect at large distances. These low-mass stars make up the vast majority of stars by number, but because they're so faint, we can only see the ones relatively nearby. To estimate the total number, astronomers must extrapolate from what they can see in our local neighborhood, assuming a certain distribution of stellar masses that might not hold true everywhere in the galaxy. There's also uncertainty about how many stars are hidden in binary or multiple star systems, orbiting so close together that they appear as single points of light. Some estimates suggest that over half of all stars exist in binary systems, while others place the fraction lower. The stellar density varies dramatically in different parts of the galaxy. Stars are packed far more tightly in the central bulge than out in the disk, and the density gradually decreases as you move outward toward the galactic edge. All of these factors combine to make star counting a statistical enterprise prone to significant uncertainty. When you see a figure like 200 billion stars, understand that it's an educated estimate with error bars that stretch across hundreds of billions of stars. Beyond the visible disk, the Milky Way extends much farther into space in the form of the galactic halo. This roughly spherical region surrounds the entire galactic disk, extending perhaps 200,000 light-years or more from the center, though defining where it ends is problematic because it gradually fades into the intergalactic medium without a sharp boundary. The halo contains very little dust and gas compared to the disk. Most of the galaxy's visible matter is concentrated in the thin disk we've described. What the halo does contain are ancient stars, both scattered individually and clustered in globular clusters. These globular clusters are spectacular objects, each containing anywhere from tens of thousands to millions of stars bound together by gravity into spherical formations 10 to a few hundred light years across. The stars in globular clusters are among the oldest in the galaxy, dating back 10 to 13 billion years to the early epochs of the Milky Way's formation. They're survivors from when the galaxy was young, and studying them provides crucial information about the conditions prevailing in the early universe. The globular clusters orbit the galactic center in elliptical orbits that carry them swooping through the disk and back out into the halo, like comets orbiting the Sun. Shapley's pioneering work studying these clusters is what first revealed that the Sun was not at the galaxy's center, because he observed that the clusters formed a spherical distribution centered on a point thousands of light years away from the Sun. The halo's most significant component, however, is completely invisible. Multiple lines of evidence indicate that the halo is dominated by dark matter, the mysterious substance that interacts with normal matter through gravity but not through electromagnetic forces, making it completely invisible to telescopes of any kind. We know dark matter exists because of its gravitational effects on visible matter. Stars in the outer regions of galaxies, including the Milky Way, orbit much faster than they should if only visible matter were present. According to Newton's laws of gravity, the orbital speed of an object orbiting a massive body should decrease with distance from that body, just as planets farther from the Sun orbit slower than planets closer in. But when astronomers measured the orbital velocities of stars and gas clouds at various distances from the center of galaxies, they found that the orbital speed stayed roughly constant or even increased slightly at large distances. This flat rotation curve, as it's called, implies that there's far more mass in galaxies than we can see, mass that must extend far beyond the visible disk in a roughly spherical distribution. Calculations suggest that dark matter outweighs visible matter by a ratio of roughly 6-to-1 in the universe overall, and the same appears to be true for the Milky Way. If this is correct, the galaxy's total mass is perhaps 1.5 trillion times the mass of the Sun, most of it in the form of this mysterious dark matter pervading the halo. The dark matter halo means that, in a very real sense, the visible Milky Way, the luminous disk we can photograph, the spiral arms glowing with young blue stars, the dense bulge at the center, is just the tip of the iceberg. The visible galaxy sits embedded in a vast sphere of invisible matter that extends hundreds of thousands of light years in all directions, perhaps even farther. This dark matter halo is what holds the galaxy together gravitationally, providing the additional mass needed to keep the disk's stars orbiting at their observed velocities without flying off into intergalactic space. The visible disk and bulge that we think of as the galaxy represent only about 15 to 20% of the total mass. The rest is dark matter, invisible and mysterious, known to us only through its gravitational influence. This realization has profound implications for how we think about galactic size. If you define the Milky Way as including all the matter gravitationally bound to it, including the dark matter halo, then the galaxy is much larger than the 100,000 light-year disk, perhaps 400,000 light-years or more across. The galaxy we can see is just the bright center of a much larger, mostly invisible structure.
At the very heart of the galaxy, approximately 26,000 light-years from us in the direction of the constellation Sagittarius, lies one of the most exotic objects in the cosmos, a supermassive black hole called Sagittarius A. This black hole has a mass of approximately 4.1 million times the mass of our Sun, all compressed into a region smaller than Mercury's orbit. Supermassive black holes of this kind appear to lurk at the centers of most large galaxies, and they play crucial roles in galactic evolution. But they're difficult to study directly because, by definition, they emit no light. What astronomers can observe are the effects these black holes have on nearby matter. At the galactic center, astronomers have tracked the orbits of stars that closely approach Sagittarius A, watching them whip around the black hole at speeds reaching a significant fraction of the speed of light. One star, designated S2, orbits the black hole with a period of just 16 years, allowing astronomers to watch it complete multiple orbits and precisely measure the black hole's mass based on the star's orbital parameters. The discovery of Sagittarius A and the detailed mapping of stellar orbits around it earned Reinhard Genzel and Andrea Ghez the Nobel Prize in Physics in 2020. These observations provided the clearest proof that supermassive black holes really exist and confirmed the position of the galaxy's dynamical center, the point around which everything else orbits. The galactic center region is far more active and violent than our sedate suburban neighborhood. Radio observations reveal enormous bubbles of hot gas extending thousands of light years above and below the galactic plane, structures that appear to have been blown out by past activity in the central black hole. When matter falls into a supermassive black hole, it doesn't fall straight in, but rather spirals down, forming an accretion disk that heats to tremendous temperatures and emits vast amounts of radiation. Currently, Sagittarius A is relatively quiet, accreting matter at a slow rate, but evidence suggests that in the past it has been much more active, possibly during periods when entire stars or gas clouds fell toward it. The radiation and outflows from these active periods can affect the entire galaxy, heating gas and potentially regulating star formation across vast regions. Understanding the central black hole and its activity history is crucial to understanding how the Milky Way evolved into its current form, because the interplay between the black hole and the surrounding galaxy has shaped both over billions of years. When we compare the Milky Way to other galaxies in the universe, we find that our home galaxy is substantial, but not exceptional. In our immediate cosmic neighborhood, a region about 10 million light-years across called the local group, the Milky Way is one of the dominant members. The local group contains more than 50 galaxies, though most are small, dwarf galaxies with only millions or billions of stars rather than hundreds of billions. The largest galaxy in the local group is the Andromeda Galaxy, also known as M31, which lies about 2.5 million light-years away. Andromeda is a spiral galaxy like the Milky Way, but somewhat larger. Estimates suggest it contains perhaps 1 trillion stars compared to our few hundred billion, and its disk spans roughly 220,000 light-years across, more than twice the diameter of the Milky Way's disk. When you look at Andromeda through a telescope, or even with the naked eye from a dark location where it appears as a faint smudge, you're seeing light that left that galaxy 2.5 million years ago, when our ancestors on Earth were primitive hominids just beginning to use stone tools. The photons entering your eye have traveled across the void of intergalactic space for longer than our species has existed. The third large spiral in the local group is the Triangulum Galaxy, M33, which is smaller than both the Milky Way and Andromeda, with a diameter of about 60,000 light-years and perhaps 40 billion stars. Beyond these 3 spirals, the local group is populated by dozens of dwarf galaxies, many of them satellites orbiting the Milky Way or Andromeda. These dwarf galaxies range from objects like the Large and Small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere and contain billions of stars, down to ultra-faint dwarfs discovered only in the last few decades through careful surveys, containing as few as a few thousand stars. Some of these ultra-faint dwarfs are so dim and diffuse that they're barely distinguishable from the background, and astronomers suspect many more remain undiscovered, hidden in the glare of the Milky Way itself. These satellite galaxies orbit the Milky Way just as the Moon orbits Earth, but on incomparably larger scales, taking hundreds of millions of years to complete their orbits. The closest known dwarf galaxy, the Canis Major Dwarf, lies only about 25,000 light-years from the Sun, closer than the galactic center itself, though it's on the opposite side of the galaxy from us. What makes these size comparisons particularly interesting is that galaxy size isn't fixed or permanent. Galaxies grow by merging with other galaxies and by accreting smaller galaxies that wander too close. The Milky Way is actively consuming several of its satellite dwarf galaxies right now, a process that plays out over hundreds of millions of years but is unmistakable in the data. When a small galaxy approaches a large one, tidal forces, the difference in gravitational pull between the near and far sides of the small galaxy, begin to stretch it out, pulling streams of stars away from the dwarf galaxy and into the halo of the larger galaxy. Astronomers have discovered numerous stellar streams in the Milky Way's halo, long rivers of stars that trace the paths of disrupted dwarf galaxies. The Sagittarius dwarf elliptical galaxy, discovered only in 1994 despite being one of the closest satellites to the Milky Way, is currently being torn apart by tidal forces, leaving streams of stars wrapped around the Milky Way like ribbons around the maypole. Over the next few hundred million years, this galaxy will be completely absorbed, its stars mixed into the Milky Way's halo, adding to our galaxy's mass and size. This is galactic cannibalism, and it appears to be a normal part of how large galaxies grow. Studies of the Milky Way's halo suggest that much of it was built up through the accretion of smaller galaxies over billions of years, each one adding its stars to the growing collection. But the most dramatic event in the Milky Way's future will be its collision with Andromeda. Despite the vast distance currently separating them, the two galaxies are moving toward each other at about 250,000 miles per hour, pulled together by their mutual gravitational attraction. Current projections suggest that in approximately 4 billion years, the two galaxies will begin to merge. This collision won't be like two solid objects crashing into each other. Remember that galaxies are mostly empty space with vast distances between individual stars.
When the galaxies merge, very few stars will actually collide with each other. Instead, the gravitational interactions between the two galaxies will dramatically reshape both, throwing stars into new orbits, triggering massive bursts of star formation as gas clouds collide and compress, and eventually resulting in a single merged galaxy that astronomers have nicknamed Milky Way. The merged galaxy will likely be an elliptical rather than a spiral, a vast swarm of stars following chaotic orbits around the common center, with little of the organized rotation that characterizes disk galaxies. Our sun and solar system will almost certainly survive this merger, but will be thrown into a completely different orbit, perhaps ending up in the outer halo of the merged galaxy rather than in a disk. The night sky, as seen from Earth, if Earth still exists in 4 billion years, will be transformed beyond recognition.
These discoveries about galactic mergers and the ongoing consumption of satellite galaxies have come largely from surveys that map the positions and motions of millions of stars. The Gaia mission has been revolutionary in this regard, providing unprecedented data about stellar motions. Before Gaia, astronomers could measure accurate distances and motions for perhaps tens of thousands of stars. Gaia has increased this to over 1 billion stars, creating a dataset so vast that analyzing it requires powerful computers and sophisticated algorithms. Each Gaia data release, there have been several major releases with more planned as the mission continues, has spawned hundreds of scientific papers exploring different aspects of the data. Astronomers have used Gaia data to map the Milky Way's spiral structure with new precision, to discover new stellar streams in the halo, to measure the wobble in the sun's vertical motion as it oscillates up and down through the galactic plane during its orbit, and to detect evidence of past disturbances to the galactic disk caused by encounters with satellite galaxies. The data has revealed that the Milky Way's disk isn't perfectly flat and smooth, but has ripples and corrugations like waves on a pond, possibly caused by a small galaxy that punched through the disk a few 100 million years ago. Beyond Gaia, other surveys have contributed to our understanding of the galaxy's size and structure. Radio surveys have mapped the distribution of hydrogen gas throughout the Milky Way and beyond, revealing that the gaseous disk extends somewhat beyond the stellar disk. Infrared surveys from space-based telescopes like Spitzer and WISE have penetrated dust clouds to map the stellar populations in the inner galaxy and have provided detailed views of the galactic bulge and bar. X-ray observatories have studied high-energy phenomena in the galactic center and have mapped hot gas in the halo. Each wavelength of light, each type of observation, adds another layer to our understanding. The Milky Way isn't a single simple structure, but a complex ecosystem of stars, gas, dust, and dark matter, all interacting through gravity and other forces, all in constant motion, all part of a system that has been evolving for over 13 billion years. Every new observation refines our picture, adding detail and nuance to what was once a simple concept of a band of light across the sky. Yet for all this progress, significant uncertainties remain. The exact distribution of dark matter in the halo is still debated. The precise number and configuration of spiral arms continues to be refined. The total mass of the galaxy, the extent of its dark matter halo, the rate at which it's accreting new material from intergalactic space, all of these are subjects of ongoing research. Even the distance to the galactic center, one of the most fundamental measurements, has been revised several times over recent decades as techniques improved. In 1985, the International Astronomical Union adopted a standard value of about 28,000 light-years for this distance. More recent measurements, particularly those based on tracking stellar orbits around Sagittarius A star, have converged on values closer to 26,000 light-years, though different studies give slightly different results depending on their methods and assumptions. This 2,000 light-year difference might seem trivial given the vast scales involved, but it affects calculations of the galaxy's size, mass, and rotation rate, showing how interconnected all these measurements are. The structure of the spiral arms presents its own puzzles. While we know the Milky Way has spiral arms, determining their exact number, configuration, and extent has proven difficult. Different studies have proposed different models. Some suggest 4 major arms, others propose 2 major arms with several minor arms, and there's debate about how tightly wound the spiral is and where exactly the different arms begin and end.
The challenge is that we're trying to map three-dimensional structure from a two-dimensional vantage point, and dust obscuration means we can only see clearly in certain directions. Radio and infrared observations help, but they trace different populations, young stars, gas clouds, older stars, which don't always align perfectly. The spiral arms themselves aren't static structures, but density waves propagating through the disk, which adds another layer of complexity. Gas and stars don't stay in the arms permanently, but rather drift through them over millions of years, spending some time in the high-density regions of the arms and some time in the lower-density regions between arms. This dynamic picture has emerged only gradually over decades of theoretical work and observation. Another frontier in understanding the Milky Way's size concerns the nature and extent of its influence on its surroundings. Galaxies aren't isolated islands. They're embedded in larger structures and connected to other galaxies through filaments of matter. The Milky Way sits in what's called a galactic neighborhood, and it exerts gravitational influence on a substantial volume of space around it. The satellite galaxies we've discussed orbit within this sphere of influence, but that sphere extends far beyond the visible galaxy. Astronomers sometimes define the virial radius of a galaxy as the distance within which the galaxy's gravity dominates over the general expansion of the universe. For the Milky Way, this radius is estimated at roughly 600,000 light-years, meaning the galaxy's gravitational influence extends about 3 times farther than even the dark matter halo's most generous estimates. Within this vast volume, the Milky Way's gravity affects the motions of everything, pulling matter inwards, capturing passing gas clouds, and maintaining control over its satellite galaxies. In this sense, the Milky Way's effective size is well over 1 million light-years across. The visible disk is just the bright nucleus of a far larger gravitational domain. This perspective helps us understand how galaxies fit into the larger cosmic web. On the largest scales, matter in the universe isn't distributed uniformly, but instead forms a vast network of filaments and walls surrounding empty voids, a structure sometimes called the cosmic web. Galaxies form where filaments intersect, and they're constantly accreting matter flowing along these filaments. The local group itself is being pulled toward a massive concentration of galaxies called the Virgo cluster, which lies about 50 million light-years away and contains thousands of galaxies. The Virgo cluster, in turn, is part of an even larger structure called the Laniakea supercluster, a collection of galaxy groups and clusters spanning 500 million light-years. In this hierarchy of structures, the Milky Way occupies a middle tier, larger than its satellite dwarfs, comparable to Andromeda, much smaller than giant elliptical galaxies in rich clusters which can contain trillions of stars, but still a significant galaxy, a major landmark in its corner of the universe. When we try to comprehend these scales, our minds struggle. Evolution shaped our brains to understand the world at human scales, distances of feet and miles, times of seconds and years, quantities we can count on our fingers or visualize in our minds. But the Milky Way operates on scales that dwarf these intuitions. Consider that light, traveling at its ultimate speed, takes 100,000 years to cross the galaxy. In the time light travels from one edge of the galaxy to the other, entire civilizations could rise and fall on Earth. All recorded human history, from the first writings in ancient Mesopotamia to the present day, spans only 5,000 years. Light could cross the galaxy 20 times over in that period. The dinosaurs, who dominated Earth for 150 million years, existed for only about 1.5 galactic crossing times. Stars on opposite sides of the galaxy are causally disconnected in any practical sense. Events happening there now won't be visible here in 100,000 years, by which time everything in our local neighborhood will have changed beyond recognition. The galaxy is so large that it effectively contains countless separate neighborhoods, each evolving somewhat independently, connected only by the gradual rotation that mixes stellar populations over hundreds of millions of years.
Yet despite these incomprehensible scales, we've managed to measure and map our galaxy with increasing precision. The journey from ancient skywatchers who saw the Milky Way as a mysterious band of light, through Galileo's discovery that it was made of stars, through Shapley's realization of its true size and our off-center position, through Hubble's revelation that it was just one galaxy among billions, to modern surveys mapping over 1 billion stars in 3 dimensions. This journey represents one of humanity's greatest intellectual achievements. We've taken something vast, beyond imagining, and made it knowable, measurable, concrete. We know the galaxy's approximate diameter, its mass, its structure, the location of its center, the speed of its rotation. We know about its spiral arms and central bar, its ancient halo and mysterious dark matter. We know that it's consuming smaller galaxies and will eventually merge with Andromeda. We know that it contains hundreds of billions of stars, and recent discoveries of exoplanets suggest that most of those stars have planetary systems of their own, meaning the galaxy likely contains trillions of planets. All of this knowledge has accumulated over just a few centuries of careful observation and brilliant reasoning. The tools we've used to probe the galaxy's size have evolved dramatically over this period. Galileo's telescope magnified by about 20 times and allowed him to see that the Milky Way was made of stars. Modern instruments can detect light from individual stars across most of the galaxy's disk and can analyze that light to determine the star's temperatures, compositions, motions, and distances. Radio telescopes can map the distribution of gas across the entire galactic disk, penetrating dust that blocks visible light. Space-based observatories operating in infrared, ultraviolet, X-ray, and gamma-ray wavelengths have revealed phenomena invisible from the ground. Specialized missions like Gaia measure stellar positions with accuracy equivalent to detecting a quarter on the moon's surface from Earth. Massive computer simulations model the galaxy's evolution over billions of years, testing theories against observations. The convergence of increasingly sophisticated observations with increasingly powerful theoretical frameworks has transformed our understanding in just the last few decades. Questions that were matters of pure speculation a century ago — does the Milky Way have a supermassive black hole at its center? How many spiral arms does it have? Is dark matter real? — are now matters of detailed measurement and ongoing refinement, rather than fundamental uncertainty. This accumulated knowledge about the Milky Way's size and structure has profound implications for how we think about our place in the universe. The ancient view placed Earth at the center of everything, with the celestial spheres revolving around us. Humanity occupied the cosmic center stage. Copernicus displaced Earth from the center of the solar system, showing that we orbit the sun rather than the reverse. Shapley displaced the sun from the center of the galaxy, revealing that we occupy an ordinary position in the galactic suburbs. Hubble showed that the Milky Way itself was just one galaxy among billions, displacing us from any central position in the universe at large. This progressive removal of humanity from any special cosmic location has been called the Copernican principle, or the principle of mediocrity. The idea that there's nothing special about our position in space and time, that we occupy a fairly typical location in a fairly typical galaxy at a fairly typical time in cosmic history. This principle has been remarkably productive in astronomy, as assuming we're not special has guided researchers away from geocentric or anthropocentric biases and toward more accurate models of reality. Yet there's a flip side to this cosmic humility. While we're not at the center of anything in particular, the very fact that we've managed to measure and understand the galaxy's immense size demonstrates something remarkable about intelligence and consciousness. We're made of matter assembled billions of years ago in stellar furnaces, arranged by evolution into patterns capable of reflection and reasoning, and we've used those capabilities to comprehend structures billions of times larger than ourselves. A typical human being is about 6 feet tall. The Milky Way is about 600 quintillion miles across. The ratio between these scales is almost impossible to express. The galaxy is about 10 to the 20th power times larger than a human. Yet humans have measured it, mapped it, understood its structure and dynamics. We're tiny, but we're not insignificant. The universe has, through us, become capable of understanding itself. The Milky Way contains hundreds of billions of stars, and for all we know, we might be the only ones who know that fact, the only intelligence that has looked up from a planet's surface and figured out the nature and scale of the galaxy spinning around them. That's a profound achievement, even if it comes from beings whose home planet is just a tiny blue dot orbiting an ordinary star in the galactic suburbs. Understanding the size of the Milky Way also provides crucial context for the search for life beyond Earth. If the galaxy contains hundreds of billions of stars, and if a significant fraction of those stars have planets in their habitable zones where liquid water can exist, then the number of potentially habitable worlds in our galaxy alone could be numbered in the billions. Recent estimates based on data from the Kepler Space Telescope and other exoplanet surveys suggest that roughly 20 to 50% of Sun-like stars have planets in their habitable zones. Even taking the conservative end of that range and applying it to the Milky Way stellar population yields billions of potentially habitable planets. Of course, habitable doesn't mean inhabited. We don't yet know how likely it is for life to arise on a habitable world, or for life that arises to develop intelligence and technology. But the sheer vastness of the galaxy, the enormous number of potential sites for life, makes it seem unlikely that Earth is unique. Whether intelligent life is common or rare, the galaxy's size ensures that if it exists elsewhere, it exists on many worlds. The distances between stars mean that we might never contact these other civilizations, even if they exist. A signal traveling at light speed from a civilization on the far side of the galaxy would take 100,000 years to reach us, by which time both civilizations might have vanished. But the possibility remains, tantalizingly just beyond our current ability to confirm or deny. The study of the Milky Way size continues to evolve. New missions are being planned, are already operating that will push our understanding further. The James Webb Space Telescope, launched in late 2021, is providing unprecedented views of distant galaxies and of star-forming regions within the Milky Way, helping us understand how galaxies like ours form and evolve. Future missions like the Nancy Grace Roman Space Telescope will conduct massive surveys of stars, mapping the galactic bulge in particular detail. Ground-based surveys using networks of telescopes are monitoring millions of stars for changes over time, building up statistical pictures of stellar populations. Radio telescope arrays are mapping the three-dimensional distribution of gas throughout the galaxy with increasing resolution. Each advance in observational capability reveals new details and raises new questions. We now know that the galactic disk has a warp at its outer edges, bending upward on one side and downward on the other, possibly due to gravitational interactions with satellite galaxies. We've discovered that the central bar is rotating faster than the disk around it, creating complex dynamics. We found evidence of past close encounters with other galaxies that have left their mark on the Milky Way structure. Each discovery adds nuance to our picture of the galaxy's size and shape. There's also growing appreciation for the fact that the Milky Way isn't static, but is a dynamic, evolving system. The galaxy looked different a billion years ago, and will look different a billion years from now. It has been growing steadily through mergers with smaller galaxies, and this growth will continue. In 4 billion years, when the merger with Andromeda is complete, the resulting galaxy will be perhaps 3 times larger than the current Milky Way, with 1 trillion stars or more. Understanding how galaxies grow and evolve over cosmic time requires not just measuring the Milky Way as it is now, but understanding its history and future. Astronomers have been able to piece together elements of the Milky Way's history by studying stellar populations of different ages and chemical compositions, identifying groups of stars that originated in smaller galaxies that merged with ours billions of years ago. The galactic halo, in particular, contains archaeological records of the Milky Way's assembly history, with different stellar streams and populations representing different accretion events. By studying the present-day galaxy in sufficient detail, astronomers can work backward to reconstruct what it looked like in the past. Perhaps the most profound lesson from our century-long quest to measure the Milky Way is that the universe is far larger, older, and more complex than our ancestors could have imagined. The ancient skywatchers who saw the Milky Way as a mysterious band of light had no conception of the true scale of what they were looking at. Even a century ago, astronomers debated whether the universe extended beyond the Milky Way, or whether our galaxy was all that existed. Now we know that the observable universe contains roughly 2 trillion galaxies, each one a vast collection of stars comparable or larger than the Milky Way. The light from the most distant galaxies we can see has been traveling toward us for over 13 billion years, showing us those galaxies as they were when the universe was young. The observable universe spans about 93 billion light-years from side to side, accounting for cosmic expansion during the time light has been traveling. The Milky Way, for all its immensity, is just one galaxy among trillions, a local landmark in an almost incomprehensibly vast cosmos. Yet for all this vastness, the Milky Way is our home in a deep sense. The atoms in our bodies were forged in stars that lived and died in this galaxy. The sun and earth formed from a cloud of gas and dust, enriched by previous generations of stars that lived out their lives orbiting the galactic center. Everything we can see with the naked eye, every star in our night sky, is part of the Milky Way, our fellow travelers through space. The galaxy isn't just something we observe from a distance. We're embedded within it, participating in its rotation, made from its substance, intimately connected to its past and future. Understanding its size helps us grasp our context, our cosmic address. Earth, solar system, Orion spur, Milky Way galaxy, local group, Virgo supercluster, Laniakea supercluster, observable universe. Each level represents a scale larger than the one before, and at each level we find that what seemed vast and all-encompassing is actually just one component of something larger still. The question, how big is the Milky Way, thus has multiple answers depending on what exactly you're measuring. The visible disk spans about 100,000 to 120,000 light-years in diameter, and about 1,000 light-years in thickness. The stellar halo extends perhaps 200,000 light-years from the center. The dark matter halo may extend 400,000 light-years or more. The sphere of gravitational influence stretches to roughly 600,000 light-years. Each of these measurements captures a different aspect of the galaxy's size, and each is correct in its own context. The galaxy contains somewhere between 100 billion and 400 billion stars, weighs perhaps 1.5 trillion times as much as our Sun when you include the dark matter, and rotates once every 225 to 250 million years. It's currently consuming several smaller satellite galaxies and will eventually merge with Andromeda to form something even larger. These numbers define the Milky Way size, but grasping what they mean, truly internalizing the scale they represent, remains a challenge even for professional astronomers. We can calculate with these numbers, use them in equations, build models based on them, but the experiential understanding of such vast scales remains forever beyond our reach. What we can grasp is the journey of discovery that led us to these numbers. From ancient humans looking up in wonder at the band of light crossing the sky, through Galileo pointing his telescope upward and discovering it was made of stars, through Shapley measuring the distances to globular clusters and discovering our off-center position, through Hubble proving that other galaxies existed and forcing us to reconsider the Milky Way's place in the universe, through decades of patient observation building up our picture of spiral arms and dark matter halos and central black holes, to modern missions like Gaia mapping 1 billion stars in 3 dimensions. Each step in this journey represents humans pushing the boundaries of knowledge outward, reaching toward an understanding of things far larger than ourselves. The story of measuring the Milky Way is a story of human curiosity, ingenuity, and persistence. It's a story of how a species that evolved to hunt and gather on African savannas developed the intellectual tools to map structures billions of times larger than their home planet. As we continue to refine our measurements and deepen our understanding, the Milky Way reveals itself as even more complex and fascinating than we previously imagined. We're discovering that it has had a more violent history than once thought, with evidence of multiple major mergers in its past. We're finding that its dark matter halo has structure, with streams and clumps rather than being perfectly smooth. We're learning that the relationship between the galaxy and its satellites is more complex than a simple picture of small galaxies orbiting a large one. Tidal forces, ram pressure from gas, and other effects create intricate patterns. We're realizing that the Milky Way is part of larger flows and structures in the universe, being pulled toward the Virgo cluster as part of the general dynamics of the local cosmic web. Each discovery adds layers of complexity to our picture, showing that the simple question, how big is the Milky Way, opens up into a rich tapestry of interconnected questions about structure, dynamics, history, and fate. In contemplating the Milky Way's immense size, we confront both our cosmic insignificance and our surprising significance. Our planet is infinitesimally small compared to the galaxy that contains it. The entire Earth could be dropped into Sagittarius A, the central black hole,
and would barely be noticed. The Sun is one ordinary star among hundreds of billions. The 1,000-year span of a human civilization is nothing compared to the hundreds of millions of years it takes the Sun to orbit the galaxy once. By these measures, we're utterly insignificant, cosmic dust pondering the cosmos. But we're the cosmic dust that ponder. We're the pieces of the universe that became conscious, looked around and asked, how big is all this? We're the matter that assembled itself into patterns capable of doing calculus, building telescopes, launching satellites, measuring parallax angles to distant stars, and deducing from all this the size and structure of the galaxy. That's remarkable. The Milky Way is vast and ancient and powerful, but it's unconscious, unthinking, unaware of its own nature. We're tiny and ephemeral and fragile, but we're aware, thinking, capable of understanding. In that sense, we complement each other, the vast, unconscious galaxy and the tiny conscious beings within it, each incomplete without the other. Looking forward, humanity's relationship with the Milky Way will continue to evolve. Future generations may venture beyond our solar system, establishing outposts around nearby stars, gradually expanding into the local stellar neighborhood. Over millennia, if we survive and continue to expand, our descendants might spread across a significant fraction of the galaxy, making the Milky Way not just the structure we observe and study, but the terrain we inhabit. The vast distances that now seem insurmountable might become highways for future civilizations with technologies we can't yet imagine. Or perhaps we'll remain confined to our solar system or its immediate vicinity, limited by the speed of light and the vast gulfs between stars. And the Milky Way will remain something we study from a distance, a magnificent structure we inhabit, but never fully explore. Either way, understanding the galaxy's size and structure provides context for our existence and our future possibilities. It's the cosmic landscape within which the human story, however long or short it proves to be, will play out. The Milky Way's size also reminds us that there are depths to reality that our everyday experience doesn't prepare us for. We live in a world where distances are measured in feet or miles, where the farthest place we might travel in a lifetime is halfway around a planet 8,000 miles in diameter. The Milky Way operates on scales 1 trillion times larger. We evolved to understand cause and effect over timescales of seconds to years. The galaxy operates over billions of years. We think of the ground beneath our feet as solid and stable. The galaxy shows us that everything is in motion, the sun and all its planets rushing around the galactic center at 500,000 miles per hour. Our intuitions mislead us when confronted with these scales, yet through mathematics and careful reasoning, we can extend our understanding far beyond what intuition provides. This is one of the great gifts of science, the ability to understand things that our senses and intuitions cannot directly grasp, to build instruments that extend our perception, to develop mathematical frameworks that let us reason about the invisible and the immense. In the end, the question, how big is the Milky Way, connects us to the deepest questions about existence. How big is the universe? What is our place in it? Are we alone? How did all this come to be? Why is there something rather than nothing? The Milky Way's size, 100,000 light-years across, containing hundreds of billions of stars, weighing trillions of solar masses, rotating once every 250 million years, represents a piece of the puzzle. It's the particular cosmic structure that gave birth to our sun, our planet, and ultimately to us. Understanding its dimensions helps us understand our cosmic context, the stage on which the drama of existence plays out. The ancient skywatchers who looked up at the Milky Way and saw a river of milk couldn't have imagined that they were seeing their home galaxy from the inside, that the faint band of light represented the combined glow of billions of distant suns, that they were participating in a grand cosmic rotation that had been ongoing for billions of years before humans existed and would continue for billions of years after. We now know these things. We've measured the Milky Way, mapped its structure, understood its dynamics, placed it in context among billions of other galaxies. This knowledge represents one of our species' greatest achievements, a triumph of curiosity and reason over the limits of perception and intuition. As we continue to study the galaxy, as missions like Gaia reveal ever more detail, as new telescopes probe ever deeper, we'll continue to refine our understanding of exactly how big the Milky Way is. But perhaps more importantly, we'll continue the journey of understanding our place within it, tiny conscious beings contemplating the vast, unconscious structure that is our cosmic home. The measurement of the Milky Way's size represents not just a scientific achievement, but a philosophical transformation in how humanity views itself. For most of human history, the scale of the cosmos was fundamentally misunderstood. The ancients believed the stars were perhaps attached to a celestial sphere just beyond the planets, maybe a few thousand miles above Earth's surface. Even as late as the Renaissance, astronomers debated whether the stars were all at the same distance from Earth or scattered at various distances. But even the most radical thinkers of that era couldn't have conceived of the true scales involved. The notion that the nearest star beyond our sun was trillions of miles away, that the band of light called the Milky Way represented a structure so vast that light itself would take 100,000 years to cross it, these ideas would have seemed not just wrong, but literally inconceivable to ancient or medieval minds. The conceptual framework simply didn't exist to think about such scales. The development of that conceptual framework required not just better observations, but better mathematics and physics. Understanding the Milky Way's size required understanding what stars actually were, which in turn required understanding nuclear fusion, which required quantum mechanics and Einstein's famous equation showing the equivalence of mass and energy. It required understanding gravity well enough to model how hundreds of billions of stars could orbit a common center without flying apart. It required understanding light well enough to interpret the spectra of distant stars and deduce their compositions, temperatures, and motions. It required understanding geometry well enough to use parallax and other techniques to measure cosmic distances. Each piece of this puzzle had to be developed, tested, and refined over centuries of scientific work. The measurement of the Milky Way's size wasn't a single discovery, but rather the culmination of countless smaller discoveries in physics, astronomy, mathematics, and technology, each building on what came before. Consider the challenge of simply determining what stars are made of. In the 19th century, the philosopher Auguste Comte famously declared that humanity would never know the composition of stars, that this was forever beyond our reach since we could never visit them or bring samples back to Earth. Yet within decades, spectroscopy proved him wrong. By analyzing the light from stars, breaking it down into its component wavelength, and studying the dark lines where specific wavelengths had been absorbed by elements in the star's atmosphere, astronomers could determine stellar compositions with remarkable precision. They discovered that stars are made primarily of hydrogen and helium, with traces of heavier elements. This knowledge was crucial for understanding stellar evolution, which in turn was crucial for understanding the age and history of galaxy populations. The bright blue stars in spiral arms are young and massive, burning their fuel quickly and dying within millions of years. The red stars in the halo are old and low mass, burning slowly enough to have survived for billions of years since the galaxy's formation. By mapping the distribution of different stellar populations, astronomers could reconstruct the Milky Way's history and understand how its size and structure evolved over time. The realization that we could determine stellar compositions from their light opened up entirely new ways of studying the galaxy. Astronomers could now measure not just where stars were, but what they were made of, how old they were, and how they were moving. The motion of stars toward us or away from us could be measured through the Doppler shift of their spectral lines. Light from stars moving toward us is shifted slightly toward bluer wavelengths, while light from stars moving away from us is shifted toward redder wavelengths. By measuring these shifts for thousands or millions of stars, astronomers could map the overall rotation of the galaxy and discover anomalies where groups of stars moved differently than expected, often indicating that they were remnant of smaller galaxies that had been absorbed. The chemical composition of stars told their history. Stars with fewer heavy elements formed earlier in the galaxy's history, when the universe was younger and fewer generations of stars had lived and died to enrich the gas with heavy elements. Stars with more heavy elements formed more recently from gas that had been processed through multiple stellar generations. By combining all this information, positions, motions, compositions, ages, astronomers could begin to understand not just how big the Milky Way is, but how it grew to its current size and what its future holds. The evolution of our understanding of the Milky Way's size also parallels the evolution of our understanding of time. Ancient cosmologies generally imagined the universe as eternal and unchanging, or at least as having existed for a relatively short time. The realization that stars had lifetimes, that they were born from gas clouds and died in various ways depending on their mass, required accepting that the universe had a history, that things had been different in the past and would be different in the future. When astronomers determined that some globular cluster stars were over 10 billion years old, this set a minimum age for the Milky Way itself. The galaxy had to be at least as old as its oldest stars. When they discovered that the universe as a whole was expanding and traced that expansion backward to a beginning point, they determined that the universe was approximately 13.8 billion years old. The Milky Way, then, formed relatively early in cosmic history, probably beginning to assemble within a few hundred million years of the Big Bang. It has spent the subsequent 13 billion years or so growing through mergers, forming stars, evolving its structure, and creating the complex ecosystem we observe today. This temporal perspective is crucial for understanding what it means to measure the Milky Way's size. When we say the galaxy is 100,000 light-years across, we're describing the galaxy as it exists across a span of time. The light we see from stars on the far side of the galaxy left those stars 100,000 years ago. We're seeing them not as they are now, but as they were in the distant past. In a very real sense, the galaxy we observe is not a single object existing at a single moment in time, but rather a collection of observations from different moments spread across 100,000 years. The galaxy now, in some absolute sense, is unknowable. By the time light from distant stars reaches us, those stars have aged, moved, perhaps even died. This temporal smearing is usually negligible on human timescales. 100,000 years of stellar evolution doesn't change most stars noticeably, but it becomes significant when we consider the galaxy's dynamics and evolution. The spiral arms we observe are not static structures, but patterns that rotate and evolve, and the pattern we see represents different moments in this evolution at different distances from us. The measurement of the Milky Way's size also connects to fundamental questions about the nature of space itself. Einstein's general relativity tells us that space isn't a fixed, unchanging background, but rather a dynamic entity that can be warped by mass and energy. Massive objects like stars and black holes create curvature in space-time, and this curvature is what we experience as gravity. On the scale of the entire galaxy, these effects become significant. The immense mass of the Milky Way, over 1 trillion solar masses when you include dark matter, creates a gravitational potential well, a warp in space-time that affects everything within and around it. Satellite galaxies fall into this potential well and orbit within it. Light passing near the galaxy is bent by its gravity, an effect called gravitational lensing. Time itself runs at slightly different rates in different parts of the galaxy's gravitational field. Clocks near the dense galactic center would tick slightly slower than clocks out in the sparse halo, though the effect is tiny. These relativistic effects are usually negligible in galactic astronomy, but they become important near extreme objects like the central supermassive black hole, where space-time curvature becomes severe. The existence of the central black hole itself raises profound questions about the relationship between the galaxy's size and its structure. Sagittarius A contains about 4 million solar masses, which sounds enormous but is actually only about 0.1% of the galaxy's visible stellar mass, and a tiny fraction of the total mass including dark matter. Yet, this relatively small mass concentration at the very center plays a crucial role in the galaxy's dynamics. Stars near the galactic center orbit under the black hole's intense gravitational influence, some completing orbits in just years or decades. The black hole's gravity likely helps shape the central bulge, and its past episodes of activity have affected the entire galactic disk through outflows and radiation. There's evidence that the masses of supermassive black holes correlate with properties of their host galaxies. Larger, more massive galaxies tend to have more massive central black holes. This suggests a co-evolution where the black hole and galaxy grow together over cosmic time, each influencing the other's development. Understanding this relationship is crucial for understanding how galaxies like the Milky Way reach their observed sizes and structures. The discovery of dark matter and its dominance in the Milky Way's mass budget represents perhaps the most profound mystery in our understanding of the galaxy's size. We can measure the galaxy's visible extent relatively well. We can count stars, map their distributions, measure distances. But the dark matter halo, which contains most of the galaxy's actual mass, remains largely invisible and mysterious. We know it's there because of its gravitational effects on visible matter, but we don't know what it's made of. Numerous experiments have searched for dark matter particles, trying to detect them directly or create them in particle accelerators, but so far all such searches have come up empty. The dark matter remains stubbornly dark, interacting with normal matter only through gravity. This means that while we can estimate the dark matter halo's size and mass distribution based on its gravitational effects, we can't observe it directly, and many questions remain unanswered. Is the dark matter halo smooth or clumpy? Does it have sharp boundaries or fade gradually into intergalactic space? How far does it really extend? These questions affect our understanding of the galaxy's total size and mass, but they're difficult to answer definitively with current observational techniques. One approach to understanding the dark matter distribution involves studying stellar streams in the galactic halo. When a small satellite galaxy is torn apart by tidal forces as it orbits the Milky Way, its stars are stretched out into a long stream that traces the satellite's orbital path. The detailed shape of these streams depends on the gravitational field they're moving through, which includes both the visible matter and the dark matter. By mapping stellar streams in detail and comparing their shapes to computer simulations with different dark matter distributions, astronomers can constrain the properties of the dark matter halo. Recent studies using this technique have found evidence that the dark matter halo might be slightly elongated rather than perfectly spherical, and that it might contain substructure, smaller clumps of dark matter, that are themselves remnants of smaller dark matter halos that merged with the Milky Way. This substructure affects the galaxy's effective size because these clumps can extend well beyond the main halo, creating a fuzzy boundary rather than a sharp edge. The question of where the Milky Way ends and intergalactic space begins turns out to be surprisingly subtle. In the visible disk, you could define the edge as where the stellar density drops below some threshold, but that threshold is arbitrary. The density decreases gradually rather than dropping to zero at a specific radius. In the halo, individual stars and globular clusters exist at various distances with no clear cutoff. The dark matter halo presumably extends to the viral radius, where the galaxy's gravity balances the expansion of the universe. But even this boundary is fuzzy and time-dependent. Beyond the viral radius, you're in a transition region where the Milky Way's gravity is still significant, but no longer dominant. The local group as a whole has its own viral radius, much larger than either the Milky Way's or Andromeda's individual radii, within which all the member galaxies are gravitationally bound together. In this sense, the Milky Way is part of a larger structure, and defining where it ends is partly a matter of what question you're trying to answer.
This ambiguity in defining galactic boundaries reflects a deeper truth about cosmic structures. They're not discrete objects with sharp edges like planets or stars, but rather density enhancements in a continuous field. The universe is filled with gas, dust, dark matter, and radiation, and galaxies are regions where this matter has concentrated under gravity. The concentration has created distinct structures, but the transition from inside the galaxy to outside the galaxy happens gradually. This is true at all scales. Clusters of galaxies fade gradually into the cosmic web's filaments, which fade gradually into the voids between structures. The hierarchy of structures, planets and solar systems and galaxies, galaxies in groups, groups in clusters, clusters in superclusters, represents different levels of gravitational organization, but the boundaries between levels are not always clear-cut. The Milky Way, despite our attempts to assign it a specific size, is ultimately part of this continuous cosmic web, connected to everything else through filaments of dark matter and gas, through gravitational influences that propagate across space, through a shared history going back to the Big Bang. The merger history of the Milky Way provides another lens for understanding its size. Current evidence suggests that the galaxy has grown substantially through mergers, particularly in its early history. Some studies suggest that perhaps half of the Milky Way's current stellar mass was acquired through mergers rather than formed in situ. One particularly significant merger appears to have occurred about 10 billion years ago, when a substantial satellite galaxy, now nicknamed Gaia Enceladus or the Gaia Sausage, crashed into the young Milky Way. This merger brought in perhaps 1 billion stars and may have helped build up the galactic bulge and thicken the disk. The collision would have been dramatic from the perspective of any civilizations existing at the time.
The night sky would have gradually filled with more and more stars from the approaching galaxy. Gravitational interactions would have disturbed stellar orbits, and bursts of star formation triggered by colliding gas clouds would have lit up both galaxies. Evidence for this merger comes from studying stellar motions and chemical compositions. Stars from the merged galaxy have distinct orbits and different chemical signatures compared to stars that formed in the original Milky Way. By identifying which stars came from which progenitor, astronomers can begin to reconstruct the merger history and understand how the galaxy grew to its current size. More recent mergers continue to add to the Milky Way size. The Sagittarius dwarf elliptical galaxy, currently being torn apart, will eventually add its stars to our galaxy's halo, increasing the Milky Way's total stellar mass slightly. The Large and Small Magellanic Clouds, the two brightest satellite galaxies visible from Earth's southern hemisphere, are also likely doomed to eventually merge with the Milky Way. These clouds contain billions of stars and substantial amounts of gas, and when they're finally absorbed, probably in a few billion years, they'll add to the galaxy's mass and possibly trigger bursts of star formation. The process of galaxy growth through mergers illustrates that galactic size is not a fixed property, but something that evolves over time. The Milky Way was smaller in the past and will be larger in the future. In 4 billion years after the merger with Andromeda, the resulting galaxy might be twice as large or more. Over cosmic time, through this process of hierarchical merging, small galaxies combined into larger ones, which combined into larger ones still, gradually building up the massive galaxies we see in the modern universe. This evolutionary perspective on galactic size connects to broader questions about cosmic evolution. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny variations in density from place to place. These tiny variations, differences of only 1 part in 100,000, were the seeds from which all structure grew. Regions that were slightly denser than average had slightly stronger gravity, pulling in surrounding matter, making them denser still. Over millions of years, this gravitational amplification built the first small dark matter halos. Gas fell into these halos, and the first stars ignited, creating the first galaxies. These early galaxies were small, perhaps containing only millions or billions of stars rather than hundreds of billions. Over time, these small galaxies merged together, building increasingly larger structures. The Milky Way represents the product of 13 billion years of this hierarchical assembly, a galaxy that has grown from small beginnings to its current impressive size. Yet the process continues. The Milky Way is still growing, still accreting smaller galaxies, still evolving. In this sense, asking how big is the Milky Way requires specifying when you're asking about, because the answer changes over cosmic time. The technologies we've developed to measure the galaxy continue to improve, promising even more precise measurements in the future. Current and planned telescopes will be able to measure stellar positions and motions with unprecedented accuracy, map the distribution of gas and dust in ever finer detail, detect fainter and distant stars, and even probe the distribution of dark matter through gravitational effects. Ground-based telescope arrays like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will monitor billions of stars, creating movies of the sky that show how things change over months and years. Space-based missions will continue to refine our three-dimensional map of the galaxy. Instruments operating at different wavelengths, radio, infrared, visible, ultraviolet, X-ray, and gamma ray, will continue to reveal different aspects of the galactic ecosystem. Each new dataset will refine our understanding of the galaxy's structure and size, resolving details that are currently uncertain or unknown. One particularly exciting frontier involves studying individual stars in incredible detail. For the brightest stars, we can now measure not just their overall properties, but also their surface features, detecting star spots analogous to sunspots, measuring differential rotation rates across their surfaces, and even detecting the presence of orbiting planets through tiny dips in brightness or wobbles in position. For increasing numbers of stars, we can measure detailed chemical abundances. not just overall metallicity, but the abundances of specific elements like carbon, nitrogen, oxygen, iron, and many others. These detailed chemical fingerprints tell the history of the gas from which the star formed, revealing what earlier generations of stars had enriched that gas through their nuclear burning and death. By studying stellar chemistry across the galaxy, astronomers can map chemical gradients and variations that reflect the galaxy's enrichment history over billions of years. Stars in the inner galaxy tend to be more metal-rich because the star formation rate has been higher there, leading to more rapid chemical enrichment. Stars in the outer galaxy and halo tend to be more metal-poor, formed from less enriched gas. These patterns help us understand how the galaxy assembled and how its size has evolved. The study of the Milky Way also benefits from comparison with other galaxies. While we have the obvious disadvantage of observing from inside rather than from an external vantage point, we have the equally obvious advantage that we can study individual stars in far more detail than is possible for other galaxies. Even in Andromeda, our nearest large galactic neighbor, only the brightest stars can be studied individually. In more distant galaxies, we can only study the integrated light from thousands or millions of stars at once. But in the Milky Way, we can study typical stars in exhaustive detail, measure their properties precisely, understand their physics deeply. This detailed understanding of individual stellar populations can then be applied to interpret observations of more distant galaxies, where such detail is impossible to achieve directly. The Milky Way thus serves as a crucial laboratory for understanding galaxies in general. Many of the physical processes we've discovered by studying the Milky Way, how spiral density waves work, how satellite galaxies are disrupted by tidal forces, and how supermassive black holes interact with their host galaxies, likely apply to other spiral galaxies throughout the universe. By understanding our own galaxy deeply, we gain insight into galaxies billions of light years away.
The practical challenges of measuring the Milky Way size remain significant, despite all our technological advances. The galaxy is simply so large that light travel time becomes a factor. Observations from opposite sides of the galaxy show structure separated by 100,000 years in time. Interstellar extinction from dust varies unpredictably, making distance estimates uncertain unless you can observe in wavelengths that penetrate dust. Stellar populations overlap in their observable properties, making it difficult to assign individual stars to specific populations without detailed spectroscopic study. The three-dimensional structure of the galaxy must be reconstructed from two-dimensional observations on the sky, a process that requires careful geometric reasoning and statistical analysis. Despite these challenges, the convergence of results from multiple independent techniques, parallax measurement, spectroscopic parallax, Seth-Voigt variables, R-Lyry variables, kinematic modeling, and others, gives confidence that our current estimates of the galaxy size are reasonably accurate, even if significant uncertainties remain. Looking to the far future, we can imagine humanity's relationship with the Milky Way evolving in ways that would have seemed like pure fantasy just decades ago. If our descendants eventually spread to other stars, the galaxy will transform from being a structure we observe and study to one we physically inhabit. The distances that now seem insurmountable might become travel routes, however slow. A civilization capable of spreading across the galaxy, even at speeds far below light speed, could colonize a significant fraction of the galaxy's habitable systems, given millions of years. The galaxy contains hundreds of billions of stars, and if even 1% of them have habitable planets, that's still billions of potential homes for future civilizations. The sheer size of the galaxy, which now seems like an obstacle, could become an opportunity. Room to grow, resources to utilize, places to explore. Of course, this is highly speculative, and it's entirely possible that interstellar travel will remain forever impractical due to the enormous distances and energy requirements involved. But the possibility exists, at least in principle, and thinking about it helps illustrate what the galaxy's size means in concrete terms. Alternatively, even if physical travel remains impractical, communication across the galaxy might still be possible. Lightspeed signals could be sent to nearby stars, establishing communication with any civilizations that might exist there.
A signal sent to a star 20 light-years away would receive a response 40 years later, slow by human standards, but not impossibly so. A network of communicating civilizations could potentially span a significant portion of the galaxy, exchanging information if not physical travelers. The galaxy size means that such a network would operate on timescales of thousands or millions of years, with messages taking millennia to propagate from one side to the other. But for civilizations thinking on those timescales, it might be feasible. The search for extraterrestrial intelligence, SETI, represents humanity's first tentative attempts to detect such signals, listening for radio or optical transmissions from other technological civilizations. So far, these searches have found nothing, but they've surveyed only a tiny fraction of the galaxy's stars. The galaxy's enormous size means that even if technological civilizations are relatively common, the distances between them might be so vast that detection remains extraordinarily difficult. The Milky Way size also has implications for the distribution of hazards and opportunities within it. Different regions of the galaxy present different conditions for life. Near the galaxy center, the density of stars is high, stellar encounters are more frequent, and radiation levels are elevated due to various high-energy phenomena. This makes the central regions less suitable for stable planetary systems and long-term biological evolution. Too far out in the galactic outskirts, the metallicity is low because fewer generations of stars have lived and died there, potentially making it harder for rocky planets and complex chemistry to develop. The galactic habitable zone, the region where conditions are most favorable for life, appears to be an annular ring at intermediate distances from the center, roughly where we find ourselves. This isn't necessarily a coincidence. If life is more likely to develop in such regions, then it's natural that we find ourselves there because we couldn't have evolved in a less hospitable part of the galaxy. This is an example of an anthropic selection effect. Our observations of where we are located are biased by the fact that we could only have evolved in certain locations. Nevertheless, the existence of a galactic habitable zone implies that the galaxy's size of structure influenced the distribution of life within it, with some regions more conducive to biology than others. The future collision with Andromeda will dramatically alter the Milky Way size and structure. Current projections, based on measurements of Andromeda's motion through space, suggest that the galaxies will begin to interact in about 4 billion years. The collision will play out over hundreds of millions of years or longer, with the two galaxies making multiple passes through each other before finally settling into a single merged system. During these passes, gravitational interactions will fling stars into new orbits, create spectacular tidal tails of stars stretching across hundreds of thousands of light years, and trigger intense bursts of star formation as gas clouds collide and compress. The supermassive black holes at the centers of both galaxies will eventually spiral together and merge, releasing enormous amounts of energy in the form of gravitational waves. The final merged galaxy will likely be an elliptical galaxy rather than a spiral, having lost the organized rotation that creates spiral structure. This merged galaxy might contain 1 trillion stars or more, making it substantially larger and more massive than the current Milky Way. Our Sun will almost certainly survive this merger. The distances between stars are so vast that actual stellar collisions will be exceedingly rare, but it will be thrown into a very different orbit, possibly ending up in the outer halo of the merged galaxy. The night sky as viewed from Earth, if Earth still exists then, will be transformed, with Andromeda stars scattered across the heavens rather than concentrated in a single fuzzy patch. This eventual merger reminds us that the Milky Way, for all its immensity and seeming permanence, is a dynamic and temporary structure. Galaxies merge, evolve, transform over cosmic time. The Milky Way as it exists today, with its graceful spiral structure and disk of young blue stars, represents just one phase in a long history that began over 13 billion years ago and will continue for trillions of years into the future. Eventually, far in the future, the merged Milky galaxy will accrete other nearby galaxies, growing larger still. Much farther in the future, as the universe's expansion accelerates due to dark energy, galaxy groups and clusters will become increasingly isolated from each other as the space between them expands faster than light can cross it. Our local group, merged into a single large galaxy, will become an island in an increasingly dark and empty universe. On even longer timescales, star formation will cease as the universe runs out of gas needed to make new stars, and existing stars will gradually burn out, leaving behind white dwarfs, neutron stars, and black holes. The galaxy will fade and darken over trillions of years. Eventually, even those remnants will decay or evaporate through various quantum processes, and the galaxy as a structure will cease to exist. But these are events so far in the future that thinking about them verges on the meaningless. For now, the Milky Way is young and vibrant, actively forming stars, evolving, growing through mergers, a magnificent cosmic structure of which we are privileged to be a part. In conclusion, the question of how big the Milky Way is opens into a rich tapestry of interconnected questions about structure, measurement, history, and our place in the cosmos. The galaxy's visible disk spans approximately 100,000 to 120,000 light-years, a distance so vast that light itself takes 100 millennia to cross it. The disk is remarkably flat, only about 1,000 light-years thick in most places, creating a structure whose diameter to thickness ratio resembles a crepe or phonograph record. Surrounding this disk is a roughly spherical halo extending perhaps 200,000 light-years from the center, containing ancient globular clusters and sparse populations of old stars. Pervading and extending beyond all this visible matter is a dark matter halo that may reach 400,000 to 600,000 light-years or more, containing most of the galaxy's actual mass. The galaxy harbors somewhere between 100 and 400 billion stars, masses about 1.5 trillion times the mass of our Sun, and rotates once every 225 to 250 million years. At its heart lies a supermassive black hole with the mass of 4 million suns. We orbit this center at a distance of about 26,000 light-years, positioned in a minor spiral arm called the Orion Spur, traveling at over 500,000 miles per hour, yet taking 250 million years to complete one orbit. These measurements represent centuries of painstaking observation and brilliant reasoning, from Galileo's first telescopic glimpse showing that the Milky Way was made of stars, through Shapley's mapping of globular clusters that revealed our off-center position, through Hubble's discovery that other galaxies existed beyond our own, to modern surveys like Gaia that are mapping billions of stars in 3 dimensions. Each advance in our understanding has revealed the galaxy to be larger, more complex, and more interesting than previously imagined. We now know that the Milky Way is actively consuming smaller satellite galaxies, slowly growing through this process of galactic cannibalism. We know it will eventually merge with Andromeda to form an even larger galaxy. We know that its visible stars and gas represent only about 15% of its total mass, with the rest being mysterious dark matter. We know that it contains a supermassive black hole at its center and sits within a vast cosmic web of structure extending across the observable universe. Understanding the Milky Way's size has transformed humanity's perspective on our cosmic significance. We've gone from imagining ourselves at the center of a small universe to recognizing that we occupy an ordinary position in an ordinary galaxy, one of hundreds of billions in the observable universe. Yet paradoxically, this humbling realization is also empowering. We are the matter that became conscious, the part of the universe that can understand the rest of it. We've measured the immeasurable, mapped the vast, comprehended the incomprehensible. The Milky Way is our home, our context, the cosmic landscape within which all of human history has unfolded, and within which our future, however long or short, will play out. Every atom in our bodies was forged in stars that lived and died in this galaxy. We are, quite literally, made of the Milky Way, children of the galaxy studying their parent. That journey of discovery, from ancient skywatchers who saw only a mysterious band of light, to modern astronomers mapping billions of stars across hundreds of thousands of light-years, represents one of humanity's greatest intellectual achievements. And the journey continues, with each new observation, each new survey, each new mission revealing more details about this magnificent structure we call home. The Milky Way is vast beyond everyday comprehension, ancient beyond imagining, and beautiful beyond words. And now, finally, after millennia of wondering, we know how big it is. This video is for educational or entertainment purposes, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.